Congratulations, you made it into the second session, and that is going to be about technology. We're going to be talking about spectrum. Well, yes, while is this all about spectrum, so you need to understand at least the high-level understanding what all that spectrum is about in 5G. We then move on to novel, exciting connectivity technologies which are being used within the 5G ecosystem. There will be some really mind-boggling technology I'll be talking about, something nobody has ever really used before in a wireless setting. We then move on to more the architecture side, the access network. Hey, how do you connect all these base stations on the roof? We then move on the core network, the really transformative way how 5G will be very different to any other G you have ever had before. Let's get started. So what are the learning outcomes of session 2? Well, I would like you to get a very solid understanding of the 5G technologies, the spectrum, what type of interface we're using, as well as the access and core network. And finally, we will spend a bit of time on the softwareization of the 5G architecture. So I would like you to understand in great details what is SDN, NFV, and slicing. I would like us to start by recapping the different bands used in 5G and what are the trade-offs. So just looking at this here, you can see we have two rough regions. One is the sub 6 gigahertz, which is 3.5 gig and below gig, what we talked about. And then we do have the millimeter wave. Anything below 6 gigahertz is very congested. It's prime spectrum because hardware is cheap. The actual deployment is quite cheap. But the problem is it's very congested. It's very difficult to find a free band of significant bandwidth which is available around the world. So we're starting to move into a millimeter wave range where you see so many more free bands available today. So what is the challenge in 5G? The challenge is to bring together so many philosophies, so many different bands, so many different ways of doing things when it comes to spectrum. So just let's have a look at the different bands. Here, 3 bands I talked about. The methods today, we have licensed, fully licensed, shared license, we have unlicensed regimes. So where unlicensed, you can do what you want as long as you obey a certain performance parameters. And the license shared approach, you need to share it with other companies in the area. So there are different ways of doing that. And then we have different aggregation methodologies. We can do a carrier aggregation per link. We can mix technologies here. Well, in 5G, that all needs to come under a single hat, because we want to support a very, very wide variety of technologies and licensing methodologies. So if you look at it from a band and licensing trade-off point of view, let's look, for instance, first of the applicability with respect to the band. So let's come back to the use cases. Remember, we had the mobile broadband, the eMBB, the IoT use case, which is the MMTC, and the low latency critical comms, which is the URL LLC. The sub gig is actually pretty good for most of these use cases. And the 3.5 gig is also very good for the use cases. But anything above that, we start to see that, but particularly to support anything related to machines and other things, becomes very tricky. Now, when it comes the application with respect to the licensing, you can see from the table that unlicensed spectrum is not suitable for the critical communications, simply because you have no control over the spectrum. Anybody could do on the spectrum what they wanted. So you can't really guarantee quality of service, QoS as we call that, and therefore it is not suitable. You need to use a licensed spectrum to do that. So let's look at one specific new technology, and that is millimeter wave. So millimeter wave is really in the high frequency ranges, anything theoretically above 30 gigahertz, but we're anything around 26 and 28 would still qualify as millimeter wave. Now, one of the downsides is that really path loss increases. So if you have the same transmission power but compared with a millimeter wave and non-millimeter wave transmitter, the range of the millimeter wave transmitter is much less. Then you have, of course, that problem that there's a huge blockage effect as you go up in frequencies. So, certain radio frequencies then stop being able to penetrate walls and windows, and they get rather reflected. Then we have the general atmospheric absorption, which leads to the higher path loss. We also have more noise because we have typically in the millimeter wave a much broader bandwidth. More bandwidth means I'm capturing so much more noise. And then because of the very highly reflective nature in some of the diffractions, we will have quite a bit of multipath visible in the millimeter wave channel. But you know what? Let's turn that from a challenge into a benefit. So let's look at the system design challenges. So propagation effects are not very favorable. So we will have a problem in terms of the network architecture because, we need to have much smaller cells to support the millimeter wave system. But at the same time, it's a great benefit. We are increasing the density of my cells and therefore giving so much more capacity to the end users. Now let's look at the signal characteristics as short wavelengths. So it means good things is we can have smaller antennas, much smaller antennas in fact, and they can be so small that we can have a MIMO array, multiple antennas on your mobile terminal in the future. And then we have, the problem with the propagation in general. You can have a lot of security features built on top of that because to eavesdrop the channel becomes very difficult because we typically have established a very strong line of sight type of capability between the transmitter and the receiver. So overall, huge challenges in the millimeter wave design, but that can be translated to fantastic benefits in the system. Let's go now to another technology, which is massive MIMO. Massive MIMO is all about, putting loads of antennas into my base station and also in the terminals. So if you look at the regular MIMO array, and you would find it if you look on the roofs of the building adjacent to you, most likely, it is a quite a long type of antenna. You typically have 3 cross-polarized antennas in there, so six antenna elements in total. And we do beamforming and all that in 4G, it's all good. But in massive MIMO, we're really upping the game here. If the massive MIMO array I have on my roof is 8x8, so 64 elements, and each of them is cross-polarized, so 128 RF channels going out. Wow, that's an increase from the 6 we have typically. And that allows us to have very narrow beams. We call them pencil beams, not only in azimuth, but also in elevation. We can do now 3D beamforming in a sense, right? So that's quite exciting. And because you have so many more channels, you essentially get a channel hardening. So the receiver perceives the channel almost Ethernet-like. So it's a almost totally constant signal once you start combining the signals from the different arrays. And then we can have a lot of interesting multi-user capabilities and have more spatial streams, and also we need to trade one with the other. So loads of opportunities once you start introducing massive MIMO. But it all came from, some interesting observation in the early days from Tom Mazzaretta and Bell Labs. And he observed that if you put the number of antennas to infinity, you can get rid of noise interference, asymptotically, and your system becomes then not a noise limited system, but not an interference limited system, but a noise limited system. So performance is much, much better. This is why we started to introduce massive MIMO. So that is how beamforming would look like. My legacy is only 2D in azimuth. Now with massive MIMO, you can have elevation beamforming as well. So you suddenly have pencil beams in 3 dimensions, giving you a huge opportunity of addressing and accessing and connecting users in particularly in urban environments. Let's talk about the interface. And similar to the spectrum observations, we need something which is unified. And really, we are trying to bring together, very different methodologies in here. So we have different OFDM configurations. We have different frame structures. We need to support advanced technologies such as massive MIMO and millimeter wave. We need to, support different duplexing methodologies. Well, for that, ideally, we would like to have a single interface, a single set of parameters you could tweak to come up with with that 5G setting here and accommodate the different technologies. And that's how we do it. So you look at the flexible radio frame design. Don't even know where to start here, but what you see is a time frequency grid. So we have the time going from left to right, and we have got the frequency from bottom up into the slide. So let's start with the the frequencies of subcarriers. You will have different subcarriers there, just as we had in 4G, but we also introduced blank subcarriers because we would like to allow maybe different systems to coexist in between or leave it for some future type of applications. We have in the time domain, different TTIs, transmission time intervals of different lengths. So again, to accommodate different requirements. In the frequency domain, we have scalable subcarrier spacing. Because as you go higher in the frequency bands, you need to make sure that your subcarriers start to be spaced further apart. As they get further spaced apart, your symbol duration goes down, so you then can adapt this by having very short TTIs. So loads of capabilities here where you have a very, very generic time frequency resource grid, which you can use to run very advanced schedulers to make that a very, very powerful interface. And a specific configuration of this all is called a numerology. So we have different numerologies here. So if you look at it today, you have different waveforms you could use, different subcarrier spacings, right? So the 15, 30, and 60 kilohertz subcarrier spacing for anything below 6 gigahertz, and then higher subcarrier spacing for anything above it. You have different cyclic prefix options, different frame durations, subframe durations, slot options, different duplexing options, physical resource block options, and the maximum number you can have, etc., etc. So a very specific choice of all these parameters is called a 5G numerology. And this is how we use it. We apply it to the radio stack. So I don't want to go into too many details, but the 3 columns you see here is for the 3 applications, the 3 use cases we talked about. One is enhanced mobile broadband, video streaming, the IoT stuff, and maybe smart grid, ultra reliable, low latency comms. So as you can see on the physical layer, we can adapt to a suitable numerology. For instance, as we go video streaming, we need a lot of bandwidth here. We optimize really in terms of coding. We have a lot of time to do that, so there's no time constraint per se. And then we can use the traditional MAC, radio link control and all the other layers on top. Now let me go to the other end of the spectrum, which is URLLC. And here we really make sure things have to happen very quickly and very reliably. So therefore the radio frame is adapted to be very, very low latency. We have a TTI, which is very short. Coding is optimized, very short payloads really, so we need specific coding for that. At MAC level, we possibly omit the hybrid air queue. The air queue is when you get your signal confirmed, your packet confirmed. If you get rid of it, then you have, of course, much less latency. So there's a different stuff of different ways of handling this today and a lot of flexibility. Of course, with the flexibility comes a lot of responsibility and comes a lot of headaches because it's to configure the system properly is very difficult. So we will have probably artificial intelligence to help us, and we're coming to grips with that. But overall, I think it's a very exciting design approach. Let's talk about the architecture. The radio access network architecture, as we used to call it, we actually got rid of the R because we think the access network architecture is more general when just supporting a specific radio. And you can see on the right hand side, on the bottom side, some true 5G base stations. We refer them as GNB. Okay, so these are the 5G base stations. They're connected between each other with an XN interface and forming essentially the access network. And the GNBs are connected to the 5G core network, which goes up on the slide. Now, on the left-hand side, you see some base stations which still have ENB in the title, Enhanced Node B, as we used to call our base stations in 4G. Now, they are not anymore called purely ENB, they're called NG-ENB. And the reason is because whilst these are 4G base stations towards the mobile terminal, they are 5G base stations towards the core network. So if a base station is able to connect to a 5G core while they're still using a 4G interface, we refer it as an NG-ENB. And it is equally connected to my 5G base stations. Let's zoom in into one of these NG next generation radio access network base stations, the GNBs. And you have different configurations. On the left side, you see a single centralized instantiation. So you have a GNB, it's literally an antenna on the roof, and it has all the processing in there, and it connects then not only to its peers, but also into the 5G core network. On the right-hand side, you see a more exciting development, and we call that the Cloud RAN, the distributed unit split. So on the bottom side, you see the GNB DU, the distributed unit, and that is my antenna. This is literally my antenna, which is on the roof, and it may have some functionalities implemented. It could do some of the processing, or maybe not. It's just sampling the spectrum and sending the whatever signal that is over the F1 interface down into the central unit, the GNB CU, the central unit, and that's my Cloud RAN instantiation, and that is where I'm doing all the processing. And I can connect several of these remote radio heads into the central unit to do the processing, and the central unit then connects to the 5G core. Why do we do that? Well, it turns out that we save a lot of energy. You need to cool your base stations. Typically, you need to provide power. So if you keep, everything very light on the antenna side and you do all the heavy processing centralized in a cloud environment, that's the best way to go. Of course, optimum would be to have it, let's say, in an Amazon web service somewhere, somewhere in a very centralized cloud, but we don't have the time of doing it because we're talking low latency. So we need to bring the cloud to the edge, and that's how we do that. Let me spend some time on the so-called functional split, which 3GPP standardized. And that can be enabled with the Cloud RAN. So if you look at, as you go from right to left, we go from the antennas, the distributed unit, which is serving our mobile terminals, down towards the left now to the centralized unit. So you have a few choices here. You could say, you know what, I'm not going to do any of the processing in the distributed unit on my roof. And I just take the RF signal, I sample the RF signal, and I send everything down to the central unit. And that would be the injection point you see here on the very right-hand side of your slide. And your data rate is just mind-boggling. You need, for an average 5G system, you need 157 gigabytes bits per second to be transmitted to the central unit. This doesn't scale really. You need a lot of fiber investment for this front hauling between your antenna and the Cloud RAN. So we said, hey, why don't we keep some of the functionalities in the antenna? And so we are splitting now, let's say at lower physical layer capabilities, assume we do the FFTs and maybe some of the coding or decoding in the antenna, and the rest goes via front hauling into my central unit. And then suddenly you see that my 157 gigabits per second have been diminished to something like 10 gigabits per second, a reduction of a factor of 10. So you see essentially as we start, processing more and more at the distributed unit, the less data rate we need towards the to get the both units connected. But of course, my latency requirement also is getting essentially better. But then my processing the benefits we get from a cloud run environment are also diminishing, right? So it becomes easier to implement, but the benefits from energy and from processing capabilities goes down. So therefore, we still need to see where do we exactly gonna split the functions, where do we do the functional split in 5G, and I think there will be different solutions to different problems in the ecosystem. Let's talk about the architecture, and that, in my opinion, is actually one of the most exciting developments. Look at this. This looks now much more like a computing architecture. You remember the computer charts we had, where you had a control plane there, which is doing all the control, and with a data bus here connecting all the control functionalities. And then you had a data plane where essentially everything happened, what the users were doing on the computer. Well, you know what? 5G is now at that point. So you see on the top all the different functionalities and functions and control functions which are needed to support anything the users want to do in the operators. So we have an application function, unified data management, policy functions, network exposure functions, authentication functions, so it would authenticate the users, access and mobility management function would take care that you get the right handovers to the right base stations, etc., etc. And they're all connected on what you can see here on a data bus, right? And then they control the data plane, which you see on the lower part of the slide, where we have a UE, a user equipment, which is my mobile terminal talking to the next generation RAN, to my base stations, which connect then straight into the data network via the user plane function. So it's become a much lighter system and much easier to implement, because you can imagine that each of these functions now could be its own software routine, and you can put it on its own virtual machine and you can do with it what you want. And that allows us to go from a very hardware-centric approach to a more software-centric one. So look on the left-hand side, this is how we used to be, 4G and before. It's all about boxes. We have base station boxes, we have the serving gateway box, we have the packet gateway box. Now that's totally replaced now by a set of software components which run on, off-the-shelf hardware. And you can see that we have the base stations connected to my Cloud RAN. The Cloud RAN is connected to the core network, but the core network runs essentially a set of servers. You can buy them off the shelf anywhere, and you just need to implement the different functionalities. And that allows us to do something now which is truly amazing, and that is entirely softwareize my 5G system. So look on the lower side, we have the actual, access, the radios. We have 5G, we have 4G, we do have Wi-Fi and anything you want to plug in. Then we have the fully virtualized infrastructure. So we had the hardware and the software decoupled, and it allows us to do network function virtualization with the VNFs, which is shown on the top left. We then have SDN. SDN is all about decoupling control plane and user plane. The control plane, if you think of an IP packet as an example, the header is the control plane, the control part, and the actual data which comes as the user part. So why do we split this? Well, it's very interesting to split because we want to support a huge amount of use cases. So think about IoT. So IoT requires, quite a bit of control, but very little data. Whereas if you want to stream a video, you have a lot of data and comparably very little control. Keeping that together, control and user data, doesn't really make sense from an efficiency point of view. So we decoupled it. We have literally a central controller which would instruct the different routers in the network to channel through the user data, and that makes it a much more efficient system. And that in overall allows us to do slicing. So the idea of then assembling functions from the NFV world and place them along an SDN infrastructure, and therefore leverage on the best capabilities of each of these functionalities wherever and whenever you need them. This is really the big breakthrough in 5G. And this is how network slicing would look like. So you see three slices here, one over the other. The top slice is the EMBB slice, so this is broadband. I'm watching a Netflix video. Then we have the ultra reliable low latency slice, so I'm need to control something in telemetry in the car. And then we have the MMTCs, the IoT slice. You're just having a sensors measuring something. Now you see then also from left to right, the actual equipment connecting to the base station, connecting to the edge cloud, connecting to the core cloud, where we have the different functionalities. And I want to explain you what this slice really means. So let's look at one specific functionality, one VNF, which is the mobility management one. On the top slice, the mobility management is in the top right corner in the core cloud. It's very far from the user. It can be very far from the user because the user is barely moving. We're sitting in a coffee shop and watching Netflix. So at the same time, I may get up at some point and start walking. So we need mobility management, but we don't need it very close to the user. So let's keep it, where we have a lot of storage and control capabilities very far in the core cloud. As we move into the ultra low latency slice, we need to support essentially a very quick handover. So my mobility management now sits in the edge cloud, right? So rather in the end cloud, it sits in the edge cloud. And for the IoT case, sensors don't move in our application, so therefore we just don't need this NFV at all. So we have just ramped it down and we're not using it. So that's the type of flexibility we get with slicing the architecture. And of course, I'm showing you three slices here with one user per slice. We will have many more slices and many more users per slices, and that will give us a lot of challenges, which I think is very, very exciting from an engineering point of view, but I'm sure we will manage. Let's talk about the migration path. So it's, 5G will not come tomorrow. So we have a legacy system today, which is our 4G system, and different migration paths have been outlined by 3GPP. So let me talk about one specific one, which I think will happen, and that's the migration from pure 4G to pure 5G. So today we have an eNode B, a 4G base station, which is talking to the enhanced packet core, the EPC, which is a 4G core network. And that will migrate to something where we have a non-standalone, 5G capability, where we have a GNB being anchored essentially to a 4G system. So you can only use the 5G antenna when a 4G system is around and anchors you from a control point of view. It essentially, instructs the mobile phone to listen to a 5G radio signal, but there's no control going on, right? So we start introducing the base stations, and then we start introducing the 5G core. And that means that my 5G base station can speak natively to the 5G core, but my 4G base station cannot anymore. So we therefore need this NG-ENB functionality, which I talked about. And then once that has been exhausted, then we go to a pure transition. We switch the 4G equipment off, and we're going purely to GNB 5G base station with a 5G core. When will that happen? We'll see. Different countries, different rollout patterns, depends on investment. Some countries will do that transition, I think, rather quickly, maybe in the next 2-3 years. Other countries will take their time. So we're talking maybe 2025, really having a global footprint of a pure standalone 5G